All right, you know me. Just introduce me. So a big problem we have is there's a lot of unknown vulnerabilities in our applications. People detect them. We have backlogs. But what if I told you that we could detect unknown vulnerabilities across entire classes, whether it's SQL injection or cross-site scripting or buffer overflows, in applications we've never seen before? We know nothing about. We just look at them and immediately know this is being exploited now, and here's where it is. You'd probably have two answers for me. You'd tell me it's magic, or you'd tell me it's bullshit. And both of those are somewhat correct. So why are we talking about this? Because there are things we can do to sort of get to this point. And it's important that we get to this point because there's no way we're ever going to close the loop on these vulnerabilities. We're not ever going to know all the things that are there. We're not ever going to find them all. We're not ever going to be able to patch them all. It's just not going to happen. So we have to find automated ways to solve this, and we have to get visibility into these applications that we don't know about. So there's a lot of types of vulnerabilities. Typically, we talk about injection vulnerabilities as things like SQL injection and cross-site scripting, command injection. But I want to define this a little bit more, and I want to expand upon what we traditionally consider as an injection attack. Instead, I want to define it a little bit differently and say it's any time an attacker supplied input changes the behavior of a victim application unintentionally. So you've written this application, and you've said it should do these things, and you take some input, and when that input is able to change what that application is doing, when it's able to change the code, when it's able to change the control flow, and introduce new paths, new code, new execution that wasn't intended to happen, that's what we're calling an injection vulnerability. And this expands what we traditionally think of it. It's no longer just like command injection, SQL injection. It unlocks stack and heap overflows, code injection, using unsafe evals, doing things like wake-up functions in deserialization platforms, which is incredibly prevalent right now in Java and PHP. All of these things are now classified as injection vulnerabilities because we're taking input and we're changing the behavior based on that input. The things we're not talking about are timing attacks inside channels, things that leak information out of the application that we can then infer. These aren't LangSec problems. Race conditions, where we're racing against other threads or processes to use a shared resource. Logic bugs. This is something that we're not ever going to fix automatically because it's based around the actual application and what it's trying to do. And you have to understand that context typically to solve those kinds of problems. Weak crypto, something that you can do in some ways, but that's really more of a platform problem. It's more of a, does your hardware support it? Does your software support it? Does your language support it? It's not about understanding input. Information leakage, weak authentication, authorization. These are all really difficult problems to solve, but we're not going to tackle them here. And these are all things that LangSec can potentially help with, but it's not a solution for them. It's not going to solve that problem for you. So I've been talking a lot about this word. What is it? There's a lot of academic definitions out there. A lot of people that really built this community up all come from an academic background. But I don't want to focus on that. I want to make something more approachable to everyone. Because one of the big problems you have is a lot of this understanding comes with understanding formal languages and compilers and parsers. And it's something that the average person doesn't know. Maybe they took a class in college once, but it's something you probably haven't thought about in years. So instead, I'm going to give a more general description of what this is. And I want to call it a methodology and technique for writing applications in such a way that user input cannot be used to change the behavior of the application in unintended ways by constraining, validating, and understanding the input and its effects. So we're going to look at this input, and we're going to decide what it's going to do. We're going to limit the scope of what is actual valid input, and we're going to reject input that doesn't meet our constraints or doesn't meet our requirements. The real thing we're going to do here is we're going to take input and we're going to think of it like a formal language. Just like you think of your source code as a formal language, that your compiler goes through and says, no, this isn't valid. There's a compiler error here. That you have to go change this. We're going to do the same thing with user input. And one of the nice things about this is it will help us by deciding what input should be valid and what shouldn't. It will help us with performance in some ways, because we're going to do all of our processing up front, which you might say, oh, it's a bad idea, then I have to do more work. But it allows us to reject a lot of input that would otherwise go all the way through the application and get to the end and be, oh, this isn't valid, I got to reject this now, and I've done all this extra work. But the big thing we're doing is we're understanding input, and we're understanding the effects of it before it happens. So why do injection vulnerabilities exist? There's typically 3 reasons, and these top three usually lead to the 4th. Insufficient or incorrect input validation, so not using the correct method, incomplete or doing it too late. Like in the case of a Stack Overflow, once you've read in that data or copied that data somewhere and you've overwritten your return pointer, that's too late. You've already done the damage. And there's very few safe ways you can get out of that once you've already done that. So it's important that we treat the input correctly, we handle it all the way through from the beginning. And then not sufficiently constraining input or its effects. So not using the right size buffers, not using the right types and putting validations in that. Making sure that the size constraints are right. If you have an integer, making sure you're not going to overflow, underflow. If you have a floating point, make sure you have enough resolution in that you can represent the number that you're actually reading in, and you don't have rounding errors. There's many more that go into this, but this is a general idea. And then the third is understanding the inputs, the effects of the input before they occur. And this is, like I said, super common when you work with evals, you work with programming languages that you can inject code into, like JavaScript, or a lot of dynamic languages that allow you to just take strings and say, this is code now. We also see it a lot in, like I said, deserialization. A lot of the time, these proprietary systems or ones built into the language, like Java, will allow you to say, when this thing gets loaded out of memory and I put it into this object, I want you to call this function and go do some stuff. There's a tool that was released a couple years ago called YSO Serial that's being used to take advantage of this. On the PHP side, there's some great talks about pop chains and using those to take execution. And the 4th is allowing input to modify or be interpreted as code. And this is typically something we never want to happen. And the reason this happens, or the reason this is so bad, is that it leads to what we're going to call unintentional Turing machines. And we'll get into that in a little bit. But it allows you to basically create a situation where you can go forward and you can execute code, and the application itself has no idea what's going to happen at that point, and it can't. With respect to incorrect input validation, this typically comes from using a technique known as shotgun parsing, which was introduced in this paper. You should definitely go read it. It's really approachable and easy to grok. Basically, what this is interspersing your parsing logic with your processing logic. So you take in a string and you start working on it. For the instance, maybe you're looking at like a JPEG file. So you read it in. I see the JFIF header. Cool. Start going, looking for some EXIF data. OK, I see this EXIF data. Keep going. And you're just going it piece by piece. And you're not recognizing the entire file. You're not understanding what it's going to do. You don't know if it's well formed before you start doing work on it. And this is a serious problem because, like I said earlier, in the case of say Stack Overflows, you get to the point where you've already done the damage because you haven't verified it first before you start working on it. So like I said, the big takeaway here is the lack of full recognition before processing. And to demonstrate, I'll go through a little example of a binary serialization format. This is nothing that's in particular. It's just something that I came up with for this demo. But we see here some data. The first byte here is an S to denote that it's a string. That's the type. The next is the size. It's 2 bytes. In this case, it's a 10-byte string. We then have some data. We see 10 A's there, followed by a null byte. And this is the end of the string, so it knows I've gotten to this point. I can now stop reading, and the next thing that I read is going to be the next string. And we can convert it to a C string doing that. So Here's a little bit of code to handle reading this in and deserializing it. Does anyone spot an issue here? OK. I'm just going to tell you. So I don't know if I have a pointer or not. I do not. So if you look right here, it gets down past reading in the size, and we start reading in the individual bytes of the string. And the way that we determine when we stop is we look for the null byte. So we've taken in the size so that we can allocate space to read this into, but we're ignoring that value. We're reading until the end of the string. And there's a lot of reasons you might want to do that. Maybe you want to make sure that you don't ever get in a situation where you stop reading and you still have data left because it's going to corrupt the next entry you read in. So you want to make sure you're always there. This isn't good code, but it's something that you might see in a normal application. So what ends up happening here is you read continually until you get to the end of that null byte, and you overwrite past the allocation you've made. So in the case of some malicious input like this, we have more than 10 A's. And we write past there. We can corrupt the stack point. We can corrupt the return pointer. And we've just crashed the program. Insufficient constraints. Most of the time, constraints are added lazily. They're responses to things that we do. We don't know what we need to accept. We just know that this thing is going to come to us. There's some input box somewhere, and data is going to come in. And we say, oh, a customer complained that this wasn't working. So you go in, you add a little bit more. You say, oh, this shouldn't happen. So you add a little bit more, and you add a little bit more, and you add a little bit more. And all of a sudden, you have this really complex logic. No one really understands what has to go there or what is allowed there. You just know that so far, I do what I'm expected to do, and it's working. So you might add in constraints for large values or weights to make sure. How many times have you seen something where you have to say, oh, just sleep for this amount of time because I have to wait for this thing to finish? It happens. So we don't think of input as a formal language. We don't know what input is supposed to look like. We just know that we have to meet all these constraints. And if we get to the bottom of it, cool, we're good. A lot of the time, you might be looking at unfriendly input. Maybe we're looking at the output of a terminal program. Maybe it's meant for humans to read and not machines. So you're going to go through and you're going to say, OK, I see that this thing I care about is here. I'm going to go grab it out of there. And that's what I need. I only need that. I don't care about anything else. Or maybe you're going to say, I know that I need to make sure this thing is here. So I see this little bit of text. And all right, I see it. Let's go. We know it's here. We know we're good. Let's just go process it now. And maybe it's not well formed, but maybe that one piece is there, and you get to go past. You also have the case of embedding languages. A lot of the time, enterprise applications or places where you need extensibility, maybe customers need to write their own business logic into your platform. You'll see people embedding programming languages. They'll embed Ruby's or Python's or Lua's or any other dynamic language because they need to provide a way to build extensibility into this platform for their customer. Well, so the problem is, what do you do with that? Do you just bring the entire interpreter in? Now you have this sandbox, hopefully, that they can do whatever they want in. And it's bad because, what are you going to do with that? In PHP, you might have people turning off certain function calls, and it happens. And that's one way people try to do it. So there's a handful of common solutions to these. The first, like I said, is sandboxing. This is really hard to get correct. Really, 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 really hard. Have you ever asked someone what functions they need access to, or what syscalls they use, or what resources they're going to use? They're going to look at you crazy. No one knows this. You go to any developer, and they're like, I don't know. I'm responsible for this little section over here. I can tell you about how we call out to Google to go pull down this data, but I don't know what's over there. Go ask Tim. And they're just not going to know. No one has the scope of the full application in their head, and especially in a large application. You're just not going to know that. Is the original author still there? Do you actually know what the vast majority of this code does? Do you even have access to the source code? These are all common occurrences. So sandboxing is this really weird technique that it works in a lot of ways, but it's really hard to get right. And we'll work across platforms. Say you're working in a multi-platform environment. Maybe you're deploying to Linux, but you develop on OS 10, or you have Windows developers. And will that sandbox work in all environments? And can you build the same rules that will go from one to the other and have those same constraints? And can you prove that? And can you prove that it's always going to work the same? So it requires a lot of trial and error. And that's the real problem here, is that you only know as much as you try. And there's a lot of unknown unknowns, which is the biggest problem that we have to solve. Is there's all these things we don't know, but we don't know them. So another technique you might use when you're doing these things is you might modify the language. Oh, I know that I don't ever want my users to create sockets or make web requests or read files. So you start ripping out functionalities like, oh, I can just take this out. Well, for dynamic languages, you really can't. A lot of this code hopefully is written natively, so it's built into, it's not written just in that language. So once you sever that connection into the language, sometimes you can kind of get away with it. But for dynamic languages, you can just introduce that code back in. Once you have code injection, once you have the ability to give it code, you just, oh yeah, you took up my network library, here's it right back. Just take it in, execute this, and cool, it's in my environment now. You also probably don't know the internals of the language as well as developers do. You probably don't spend all your time working in it. This is maybe something you spend a day doing, a week doing, a month doing. But it's not your focus. Your focus is making sure that this application is deployed, that it's running, that your feature set that you're responsible for works. And because you're doing this, you're not taking upstream patches. When vulnerabilities are patched, you're not going to take those in. Maybe you've modified it a bunch, and you can't just go start applying those patches, or you can't just upgrade the version to something new, because it's going to break everything. It's not going to work. Your sandbox is going to disappear, and it's not a viable option. So what's the real problem here? What are we really trying to solve? And in order to understand this, we need to understand a little bit about computational theory and the machines that do it. The machines that understand language, that are able to comprehend it and make decisions about language. So this is where that automata theory class you took all those years ago, assuming you did, is going to come back to haunt you. And we're going to dive a little bit into this. So there was this guy, Noam Chomsky, and he developed this hierarchy of languages. The bottom here you see regular, and the top you see Turing complete. So every higher level language has more power. It's able to do more things, and every higher level language encompasses a lower level language. So the regular languages are the least powerful, where the Turing complete languages are the most powerful. In the case of one of your standard programming languages like Ruby or Python or Java, these are all Turing complete languages. And we'll dive a little bit into what that means in a minute. Regular languages and context-free languages, this is what we want to shoot for. This is what we want to shoot for when we design our input and we start constraining it. Because it's going to give us a lot more freedom and a lot more power to say, this is invalid, this is what it's going to do, I know this is bad. So in order to just get to kind of draw a connection between languages and the machines that recognize them, and that's what we're going to start doing now. So there's a main difference between context-free and regular really comes down to two things. And there's a whole bunch of complex stuff you can go look up. You can look up proofs. You can look up a whole bunch more about this. But it really comes down to two things. One is you're always moving forward. You're not going to move back on the input. You're not going to rewind. You're not going to do any of that. You also can't, with regular languages, you can't match things. And what I mean like that is you can't match, say, an opening tag and a closing tag, or an open paren and a closing paren, other than doing maybe one level of it. And we'll see why. So you might recognize the top part here as a regular expression. This is typically how you would refer to a regular language. The machine that is capable of computing a regular language is called a DFA, or a deterministic finite automata, or an NFA, a non-deterministic. And they work mostly the same way. There's a proof that says any NFA you can convert into a DFA. So really, we're just going to focus on DFAs for right now. And this is essentially a state diagram showing what this machine does. And this could be any kind of machine. It could be built out of wood. It could be built out of toothpicks, as long as it could represent these states and the flow through the thing. You'll see here we have two types of circles. We have these open circles that have nothing else in them, and these two-ring circles. The open circles are a normal state. These are non-accepting states, and the double circles are accepting states. If you're reading an input and you don't get to an accepting state, that input is not a valid sentence in that language. So maybe you haven't finished all the way, but you get to the end of the input, it's not valid. So in the case here, it's a really simple state diagram. That's the equivalent of the top regular expression. We come into state 0. We're going to match 0 or more of the letter A. We'll then move forward, and we're always going to match a B. There's at least one B. And then we're going to look for the D or the F. And we're going to match at least one and as many more as we want. And both of those are accepting states. So if we get all the way through this and we get to one of those states, we know it's a valid sentence in the language. Moving forward up to context-free, typically you will describe these in something called a context-free grammar. I didn't put a slide together for that because it's kind of hard to demonstrate. But instead, I'm going to show you a PDA, or a push-down automaton. This is another type of machine. This machine is very similar to the one we just saw. It is a state machine, just like the DFA and NFA, only this machine has a stack. It has memory, which the other one didn't. The other machine, the DFA, knew nothing about what we've already seen. All it knows is, I'm right here, I can go to these places, and I can only go to these places. If I can't go to any one of these places, it's not valid, and I stop. This type of machine uses a stack to understand a little bit about context and know where we are in this. So in this case, I'm going to build a really simple parser for something like a scheme language or a Polish notation calculator. We see at the top the simple string we want to match. Just like before, we're coming in to state 0. The difference here is that we're no longer specifying just what we're looking for. We now have this delta function. And this is the function that's going to run on every single transition from state to state. The first parameter right here, this is what we're looking for on the stack. So every time we take a transition, we're going to pop off the stack if this is an epsilon. And we're going to look and see what's there. If it is epsilon, we're not going to do anything. It's a no-op. But if it's not epsilon, we're going to look at that. If it's not that, it's not a valid transition. If it is that, and it's a valid transition, we're going to then push this onto the stack. And that allows us to keep track of things like how many levels of parenthesis we are deep, how many tags deep we are in an HTML document. And we can use that to make sure that we always close our opening tags, we always close our parentheses, and we can know that we've not gotten to some weird state. So to walk through kind of how this works, we're going to start at state 0. We come in, and we are going to push this $sign onto the stack. We're not looking for anything up here. We're not looking for anything on the stack. We're just going to push it there. And that's our end of string marker. It's how we know when we got to the end. When we get all the way down the stack and we see that, we know that we're at the end. And if we're not at an accepting state, we know it's broken. We know it's bad data. So we come through, and we're in state 1, and we're looking for an opening paren. And we see it. So we push that opening paren onto the stack, and we move into state 2. Now we're looking for either a plus sign or a minus sign. We don't care what's on the stack. We're not going to push anything onto the stack. We just want to know that there's a plus sign or a minus sign because we're looking for some kind of operation that we're going to compute. And we see it. So we move into state 3. We're in state 3, and now we're looking for a lot of things. We're looking for either a closing paren, because we are at the end of an expression. We're looking for any numbers, 0 through 9, because we're looking for numbers to compute this. And we're also looking to go back into state 1, because we can go grab another nested expression and put that in there to compute first. In this case, we're going to see the transition to state 1. We're going to see another paren. So we push it onto the stack, and we move into state 1. We're going to go back, and we're going to replay the same thing, and we're going to keep going forward. We're in state 2. We find the minus sign, move into state 3, and we're looking for numbers. We find them. And now we're to the point where we see the closing paren. And so we're going to pop off that opening paren, and we're going to push nothing onto the stack. And we're going to do it again. We're in state 4. We're looking for a dollar sign. We move into the accepting state, and we're done. This is a valid string. It's a valid sentence in this language that we defined. So this is a machine that can recognize that. And like I said, it can be built out of anything. It doesn't have to be software. Anything that can represent those states, the transitions between them, and enforce those rules and to provide a stack or some kind of means to store that data in a stack-like system where you have last in, first out. That's all the requirements are. As long as you meet those two requirements, you can have that kind of machine. So does anyone know what this is? What was that? Sort of. This is a model of a Turing machine. So in the 1930s, this guy Alan Turing and this guy Church each kind of worked on their own directions, trying to do a lot of work in defining a formal system for what algorithms are and designing machines that are capable of running them in a general sense. So a machine that could run any kind of algorithm and be programmatic. There had been some programmable machines before, but not universal ones. And this is the main thing that he was trying to do. So this is what most modern day computers are based on, this principle of a Turing machine. And the way that this works is you have this tape. And you put the tape in, and it will read each mark you make on it, and it will compute it. So you put the program in, it reads the program, and it does what it's programmed to do. There's also what's called a universal Turing machine, which is capable of simulating all possible Turing machines. And this is really what we're going to move into next. And so the main difference between DFAs and PDAs and one of these is that these can move forwards and backwards. It might get into a state that says, I need to go backwards, and it will read back of the tape. And it can erase the tape, and it can rewrite it. And it can change the code that it's executing. It can change the algorithm that it's designed to build. And this is what we're trying to stop from happening. This is what we'll eventually see is what we're modeling as one of these. And this is bad. So the unintentional Turing machine is what we're creating. By taking an input and not validating it, by allowing the user to provide input that we then execute, that can change the behavior application, this is creating an unintentional Turing machine. We're giving unintentional power to the attacker for them to use our application as a platform to do what they want to do with it. There's also this concept of recognition and decidability. Recognition is the ability to say, yes, this string is a valid sentence. No, this string is not a valid sentence. It's not saying I know what it's going to do. It's saying I know that this is a valid sentence in this language. Decidability is the ability to take that and say, this is valid or not valid, but I know what this is going to do. I know that if I were to take this input with this algorithm, that it's going to do this. It's also the ability to say, I can take this algorithm, and based on what it does, I know it's always going to stop. This is always going to end. And I can prove that based on the fact that I know what the input is going to do. And this leads us into the halting problem, which is one of the big problems in computer science. So imagine that our input is a program that contains a dynamic loop. We're taking an input, and it's going to say, I need you to do this until the number specified in the input is reached. Using what we've now learned, we can recognize that this input is in fact valid or not valid. So we can say, OK, this looks like a valid program. I'm going to go ahead and run it. But we'll never be able to say for sure that this program will ever finish running or what it's going to do, because we don't know what that arbitrary number is going to be, at least in most cases. So there's no generalizable algorithm that exists or can exist to solve this problem. And the reason that we can't do that is, say, for instance, we have this loop, and it hasn't finished executing yet. Well, has it not finished executing because we have more processing to do? Is it an infinite loop? How do you determine which one of those is the case? And the short answer is we can't. And so the other thing to note here is that Turing machines as a whole are undecidable. We can't write an algorithm to do this. For DFAs and PDAs, they typically are. We know all the state transitions that are going to happen. We know what's going to go from state to state, and we can say, by proving it, this will exit or this will not exit. So what's our solution to this? And we have a few that you can kind of mix and match, and we'll kind of see where the limitations of those are. So let's think about all input as sentences in a language. Whether it's code to be executed, whether you're taking in dynamic code that's going to get run, or it's simply data that we are going to use in our application to make some choice about, to do something with, to transform. There's an alphabet. We have grammatical rules. And we go through and we verify that the input matches that. And then fully recognize the language and verify that it's a valid language, it's a valid sentence in the language before we go ahead and process it. Design the minimum language that's required. Like I said earlier, embedding an arbitrary interpreter, it's a bad idea. What's the minimum that we can get away with? What kind of functionality? Do you need the ability to go create loops? Do you need the ability to call arbitrary functions? Do you need the ability to call out of the application to an arbitrary library? What's the minimum that we can build that we know that we can constrain so that we don't have to make all these difficult calls as to whether or not it's dangerous? And favor sub-Turing when you can. Create a language that's not Turing complete just for the possibility that you can prove and say, hey, this isn't going to be something that I can't decide about. There's a bunch of tools out there to help you do this. If you want to build your own state machines, there's a tool called Regal. You define in a DSL kind of your state transitions and all your states, and it will generate you code in any language you want. There's a really popular HTTP parser from this web server called Mongrel that's basically used everywhere. It's extremely fast because it can accept and reject input immediately based on whether or not it's correct. It's really performance because of how it's written, and it can recognize things very quickly. But it's also just very easy to prove. And you can go through and you can see, this is exactly to spec what the parser should do. Rather than saying, OK, I see this verb I have to look for. OK, cool, it's get. Here's a path. This looks correct. And then verifying every single header there that's correct. If you want to do regular expressions, PCRE is one of the most common, as well as RE too. They're in everything. If you're using regular expressions, you're probably using one of these. There's also POSIX, which is pretty much supported everywhere, but nowhere near as powerful as PCRE or RE2. So I definitely go with one of those two. And then there's parser generators. For more complex languages, like the ones that context-free grammars require, there's tools like Yak and Bison. These are ancient, and they work everywhere. You can build it for any language you want. And they're easy to use. They're really powerful, and they're pretty performant, just based on the algorithm they use to do the matching. We at Previty use Antler. We like it a lot. It doesn't have the support that Yak and Bison do. Java and .NET are first-class citizens. There's also versions for JavaScript, Ruby, Python, I believe a couple others as well. But it's really nice. It gives you full parse trees. It provides you a system for walking your parse trees and working and transforming and working with that data. If you're working with binary data, you probably don't want to use any of these. And you probably want to use something like Hammer or Nom. Hammer is written in C. It's a parser combinator library where you can write functions that recognize individual things, and you compose these functions together to build up your parser. Nom is another one, similar, and it is written in Rust. As far as I know, there's no bindings out of there, but there could be. So if you wanted to write, say, in C or C++ or build bindings to it from any other language, you could totally do that. But it's really powerful. And when you're using it for like binary data, like taking in serialized data, or maybe like wave files, or you're looking at audio files, all the things that came from like lib stage fright and all these Android bugs that came out, this helps solve some of those. Because you know what the data looks like. You know whether it's valid, and you can reject it before you start doing things with it. VLC actually just started writing a few of their parsers, some of their file formats in Nom, and have shipped actual code with it, and have shown serious performance improvements and shown significantly better quality parsers that they know aren't broken. The other is separate code from data. Don't use functionality like eval. There's almost no excuse to ever do that. Just don't do it. Utilize functionality like write XOR execute. This is a pattern of marking individual pages in memory as either writable or executable. You can never have both. It's one of the big solutions that people have introduced in operating systems when you like to stop memory corruption. A lot of the ways people exploit that is by writing shellcode in memory. If you can't execute that code, you're a lot less powerful. And there's ways around that, but it's a big step in making it more difficult to do, which is what we're trying here. So what about the case when static isn't enough? We've been talking a lot about looking at static data, looking at input statically. That is the full context of what we're looking at. And LangSec isn't a magic bullet. It's not going to solve all your problems around input validation. It just can't. Sometimes we have input that's dependent on context. Maybe there's application state that we don't have access to. Maybe there's some config file somewhere. We don't know. And we can't look at input that way. We can't know. And this isn't to be confused with a context-sensitive language, which we didn't really cover. It's just the presence of context that determines what's going on. So in this case, you can utilize safer languages. Utilize symbolic execution, emulation, taint analysis. Look at data going through and analyze what it's looking like. And we'll see a little more how to do this. So like I said, solving the halting problem. We can't do it. There's no way to do it. And we will never solve this problem. Unless there's some major changes to computer science in the future, it's not going to get solved. But we can do things to avoid it. We can get around it. We can make assumptions. We can specify syntax that's not allowed. We can insert time limits. We can block access to resources, syscalls, functions. It's things that we already said, like it's hard to get that information, but it's something that we can do. We can build sandboxes. We can do this. We can recognize syntax. We can say, hey, I see you're calling this function. This function isn't good. We can't decide whether or not it's good or not, but we can say, we can't decide universally whether it's good or not, but we can say, I know this is bad and I don't want that there. And so we create these artificial constraints. And so you might ask me, what about legacy apps? I didn't write my application with LangSec in mind. I can't do anything about this. All these things you just told me are useless. But it's not true. There's a lot of things you can do. A lot of application platforms have ways to introduce things like introspection or have performance APIs that allow you to hook into it and work with it to look at what's happening in the application. So you can build tools around this functionality, and you can inject it into the application after the fact. Really quick, I'm just going to go through. There are a handful of applications of products out there that do these things. If you're going to be using one of these, ask them questions. They should be able to tell you all these answers. What are my environment? What's the supported environment? Performance metrics. What's it going to do to my application? Where is it operating? Does it have the context it needs? Is it operating at the network layer, but it requires more information that's not available at the network layer? What about the halting problem? Does doing their thing that they say they do require solving the halting problem? If it does, what assumptions did they made? How did they bypass that? What were they able to do to solve that? So to conclude, think about your input as a formal language. Recognize and validate your input before processing. Constrain your input as much as possible. And the halting problem can't be solved, but that doesn't mean it's the end of the line. We can do things about that. We just need to be smart about it. Cool. Thank you.